What we're going to take a look at in this video is the real-world applications of exponential functions. And we're going to see they really do come up in a lot of different situations. A lot of these are going to be formula-based, and all those formulas should be on the guided note sheet that is distributed to you. So if I take a look at that and kind of what we got up on the board here, when a real-life quantity increases by some fixed percent each year or some other time period, the amount y after t years can be modeled by this equation that I have going on here, where the few of these things mean different things. A stands for the initial amount of whatever's growing. So what we could take a look at, say, is if we invest money in something, say we put $100 into a bank account, we want to see how much money is earned through interest after a certain amount of time. That A value is going to be the initial amount. If I'm talking about a population either growing or decreasing, the initial amount that I start with is going to be my A value. That's what A stands for. T in this equation, which is in the exponent here, that T value stands for time. Typically that's years. If it ends up being months, it'll be specified in the problem. If it ends up being hours, it's specified in the problem what T is going to be. Usually it's going to be years though. And just looking at this structurally, when I write all of this out, T is an exponent, A is basically a coefficient in front of this term, 1 plus R. The 1 is always going to be there. All right, that does not change. And then R stands for the rate. So at what rate is our substance increasing or decreasing? So in a lot of questions we're going to be talking about exponential growth. What you'll see is there should be a plus sign in the middle here. That there should be a plus sign if we're growing. If we're decreasing or decaying, which we'll get to later in the video, there should be a subtraction sign there. And then R just stands for the rate. Now, before I kind of get into actual examples of this, which will make more sense of these variables, an important thing to look at is right here. You know, some questions are going to ask you for a 5% increase, a 19% increase, or an 100% increase, but we don't write that in this equation up here in terms of the percent. We're going to put it in terms of a decimal. So instead of writing 5%, what we're going to do is, just like anything, we would move the decimal place 2 to the left. So really, we're going to write 0.05, because that's the same exact thing as 5%, moving that decimal place 2 to the left. So if I have 19, I would take my decimal, and I'm going to move it 2 to the left. 1, 2. So instead of writing 19%, I'm going to write 0.19. If I had 100, I'm going to start at the end, move 2 decimal places, so I would put a rate of 1.00. Okay, and what that's called, that 1 plus R, is called the growth factor. So it's going to be, what am I multiplying my original amount by to see how much is going to end up increasing. If it's 1 minus R, it'll end up being the decay factor. So when we take a look at these, that's kind of an important piece, which is going to make sense when we look at this example. So in August of 2005, there were around 50,000 people who attended the Little League World Series. During the next 4 years, the attendance increased by 97% each year. So first thing we want to do is write a model giving the attendance after a certain amount of years. So I want to find out the attendance. Our base formula for this is going to be our exponential growth formula. Our growth formula is the one that we were just talking about on the last slide. So we want to go through and fill everything out. Now we have to match up the pieces for this. So A, our initial amount, 50,000 people. That's the amount of people there were the first year. That's going to go at this part of the formula. So I would say 50,000. Looking at the rest of this, we see we have a rate of 97%. So what that's telling me is that my value on the inside here, it should be 1 plus 97%. And remember what we said, when we have 97%, we're going to write that as 0.97. We're going to move that decimal place 2 to the left, so it'll be 1 plus 0.97. Right now, we're saying to the T because we're just writing a model for this. We don't know what that T value is going to be just yet. So if I'm going to kind of just simplify a thing or two, that's going to give me 1.97 raised to the T. So just kind of adding that 1 and the 0.97. That would be my basic formula that's going to tell me, A, how many people have attended after a certain amount of years. So if I want to find out how many people attended 5 years later, I would plug in a t-value of 5. Now looking at question B, it says how many people were in attendance at the Little League World Series in 2007. That's 2 years after 2005. So what I'm going to end up doing is I'm going to take this whole formula, 50,000, 1.97, and raise that to the second. Because if I raise that to the second power, what that's going to end up doing is it will tell me really how much it's grown over the course of 2 years. Because if I think about what this is really saying, it's 50,000 times 1.97 and then times 1.97 again. So if I think about that, this piece here just goes through and tacks on 97% once. That would be 1 year. Then whatever that answer is, I'm really multiplying it by 1.97 again to add on that second year of adding 97%. So I'm going to go into my calculator, I'm going to plug all of this in. And when I go through and I do that, I get 194,045 people. So what that's telling me is if I just plug all that in 2007, that's how many people would be attending the Little League World Series if I increased by 97% each year. So that would be a typical growth question. Anytime it just talks about growing, and that's all it really says, we're increasing, something like that. Now, the next kind of example we could have is called compound interest. If you put money into a savings account and they tell you you're going to earn interest on this amount, they're basically giving you a percentage of the money just for having your bank account with them. You kind of earn money on whatever you have already in the bank. Now, this is going to be very, very similar to the exact equation that we just kind of looked at. And it should looks different right now, but it's saying the same things. If I look at this, I have some y value equal to my initial amount. Here they call that initial amount P, so principal they say. It's the same exact thing. It's the initial amount, whatever amount of money you start with. What's different here, my rate is still the same. My t value up here is still the same. What changes is these n values, these things, okay? When I go through and I look at this, when I write it, 1 is still the same, plus I have a fraction here, r over n. Now in the exponent, I have n times t. So I'm going to have my n value times t. All of these things are the same. Initial amount. We have our rate. We have our time. Now, what the n value stands for is the number of times per year that the interest is compounded onto the amount. So n here and n here are going to be the same thing. It's going to be how many times per year interest is added on. All right, so how many times per year? So if I go through and I look at these, if I look at A, my n value would be 1 because it's compounded yearly. 1 time per year, the 8% interest in this question is added on. Quarterly, if I think about how many times that's going to happen per year, it would be 4. There's 4 quarters in $1, 4 quarters in a football game, whatever I think about. I'm going to get that done 4 different times throughout the year. And then daily, we'll just kind of assume there's no leap year here. We'll just go 365. So looking at this question, we deposit $1,000 to start. So that's our initial amount. And it pays 8% interest. All right. So those are our key values. Now we want to find the balance after 1 year. Another key piece of information. If the interest is going to be compounded with the given frequencies. So we're going to have 3 different questions here. We're going to go through and really fill out the same thing. So I'm going to have y equals, my initial amount is 1,000. Then I'm going to fill here 1 plus my rate. Looking at that, I have 8% as my rate, so it would be 0.08. How many times is it compounded per year? We said once. My n value is 1 here. Then I would go through, my n value up here is 1, multiply that by 1 because we have a t value of 1 right here. And I go through and I plug all of this into my calculator, which gives me, 1 second, because I got to just double check, make sure. Oh no, that was 1,080. All right, so that's what I would get if it's compounded once per year. Now, I'm going to go through the next two questions in a second, but what people kind of get confused on this is just what makes this different than this. All right, anytime you see the word interest, that's a trigger for this kind of equation, the compound interest equation. So anytime you see interest, you should kind of just, in your brain, that should just be a red flag. I have to use the interest equation. And then I'm going to go through and do these other ones as well. Again, these are interest-related questions, so I should use the interest formula. I'm going to go through and plug everything in the same. 1,000 still my initial amount. 1 still goes here. I'm gaining interest. My rate is still 0.08. Now, I'm doing this quarterly, so my end value is 4. That's how many times per year I'm accumulating the interest. Now, in the top up here, n times t would be 4 times 1, because 4 is my number n, and then that's how many times I'm compounding per year, and then 1 is the time. So I'm going to plug all that in my calculator, and I should get, we're in 2 decimal places, we're talking about money here, so we should get $1,082.43. And if we think about it, if we look at it, it's different than the yearly one, all right, because I'm gaining interest twice, or sorry, 4 times. It's going to end up kind of earning you a little bit more money. Now, the last one, daily, going to be the same process. 1,000, 1 plus my rate is 0.08. 365 is the amount of times I compound per year. 365 times 1 up there. I'm going to plug that all in my calculator, which this one I actually have to go through and plug in just to double check. All right, and I should get $1,083.28. Yeah, that's what I should get into here. Now that tells us, and again, we're talking about money, we can throw the dollar sign on there, and we would be all good. This is an interest kind of question, so anytime I see interest, that's the trigger word here. Anytime I see growth without the word interest, that would trigger this equation. And the last one, anytime you see the word decreasing, all right, anytime you see decreasing, you should think about decay. Talk about losing something. Now, all of this stuff is the same. That should be 1 minus R. All this stuff is going to be the same. You know, A is the initial amount, T is the time, R is the rate. The only thing that's changed, we were talking about decay or decreasing, so we should have a negative here. So we should be, you know, we're going to do 1 minus whatever our rate is, which is called the decay factor. Now, looking at the same way, if I have a 5% decrease, I'm not going to put 5%. I'm going to put it as a rate. I'm going to put 0.05. By a 0.19 decreasing, you know, my rate's going to be 0.19. If I have a 100% decrease, which is just taking the whole thing away, out of a 1.00 rate that I would actually plug in, because remember, we're using decimals here. Now, what the question would kind of look like is this. You buy a new car for $24,000, the value of Y on the car decreases or depreciates, or any of those kinds of words, decays by 16% each year. So first thing, we want to write a model after t years. So it's a decreasing equation. We should immediately trigger this formula. And it's going to immediately be that. And I just fill in all the missing parts. A is my initial value, 24,000. Now I would go through and I would say 1 minus my rate here, 16%. I'm not going to put in 16%. I'm going to put in 0.16. So I plug in 0.16. All of that is raised to the t. To kind of clean things up a little bit, we will say 0.84 to the t, because that's what 1 minus 0.16 would be. Okay, again, decreasing, it should trigger this equation. Decreasing equation, A is my initial amount, R is my rate in a decimal form, and then T is the number of years that we're looking at, or for whatever the question is. And part B gives us that amount. So we're saying 2 years. Now what I'm going to go through and do is I'm going to plug everything in. So I would say 24,000, 1 minus, I'm sorry, I could just say 0.84. To the second power. All right, so we're talking about 2 years here. So I'm going to go through and I'm going to multiply these terms. So 0.84 squared. That should give me this. 16,000. Okay. So this amount here, $16,934.40, would be the amount that your car is worth if it started at $24,000 and it decreased by 16% each year after 2 years. Losing about, a little over $7,000 on the value of the car. That's what kind of happens with these things. So that's all of the examples that we have here. And really we could take a look at this last one. It gives you a formula now. So it's saying we have this, we have some iodine 131, and it's given in this formula. And now it's kind of asking us to interpret it. What is the initial amount of the substance? If I look at that, we should be able to identify what that is. Okay, so hopefully you can write that down. Give you a second to do it. It should be 50. That's this value right here. It's always going to be that first kind of coefficient looking thing. Now, what percent of the substance decays each day? If I take a look at that, I need to look at the decay factor. So I have a decay factor of 0.92. What that's telling me, remember, is the decay factor is 1 minus my rate. So I need to figure out what's the percent that I'm decreasing by. So I can rewrite this as 1 minus 0.08. Okay, that's the same exact thing as 0.92. And because remember, everything that we started with, all of those equations were in this format, where it was 1 minus something or 1 plus something, that was a rate, that was a decimal. And in this case, I can say, well, here, 1 minus r would be 1 minus 0.08. That means my rate is 0.08. My rate is 0.08. That means it's really the same exact thing as 8%, which is just what the question is asking. It's asking for the percentage that we're looking at. And that's what it would be looking for there. I'll give you guys a few problems to practice all these different things. To sum it up, there's 3 different formulas. There's a growth formula that we started with. That is here. Okay, and remember, all that A, R, and T all stand for the same thing no matter what. Trigger words here are growth, increasing, what have you. All right, next one is the interest formula. When you see the word interest, it triggers that because it's always going to have some amount of time that you're compounding interest, whether it's yearly, daily, quarterly, semi-annually, monthly, whatever. You got to think about that end value is how many times per year am I actually accumulating the interest. And the last one is decay. And again, all this stuff is the same. What's changed is now there's a subtraction sign in the decay factor, instead of it being an addition sign, making it the growth factor. And that's all.